Hi, Lindsay. So in today's lesson, we're going to look at two examples. First one, we're going to be looking at given a graph like this, then we're going to create two equations, both sine and cos, related to this. And our second example is going to be an application style question where we're going to be given some info and we're going to be graphing this as a sinusoidal model and using some interpolation and seeing, an internal height. Okay, so let's start off with our first example here of determining two equations for the sinusoidal function shown. So there's two ways that we can write this in general form. That was using our sine and cosine. So we have f of x is equal to a sine of k x minus d plus c. And the other one that we could choose, sorry, we don't need that bracket there, is using cosine and how it relates to this shape here. So remember, just in general, that our sine started at the origin here and went up and then went down, something like this. And then cosine started up top and it went down and then it went something like that. Okay, so those are the two shapes. Again, this is for sine x and this is for cos of x. That we're going to look at this and split these into different parts to resemble these equations here. Okay, so the first place that you can start with is, let's see, why don't we start with our, well, what we can do is determine some elements that are going to be similar for both. So for example, this axis of curve will be the exact same for both. So this axis of curve here, C, is going to be the maximum plus the minimum divided by 2. Okay, so that's the maximum plus the minimum divided by 2. So in this case, our C value is going to be 3 plus -1 divided by 2, and that's going to give us a value equal to 1. So right here at this value of 1 is where this is going to be the axis of curve. It's going to be split exactly in half. So from the amplitude, which is right here, I find it easier just to look at the graph because we can see if we go from 1 to 3, well, that amplitude, that difference there is equal to 2. Same thing if we go from the axis of curve to here, 1 to -1 is that value of 2. So in this case, we can see that the amplitude is equal to 2. So that's already this variable and this variable here. So the next one we can look at actually is this k value. So remember that k is equal to 360 over the period. Always, always in general, this is our equation. So the period is where we have these repeating points. So for example, we can look at the peak to peak. Okay, it goes through this shape and then it starts to repeat. So this right here represents the period. So if we go from 10 seconds to 20 seconds, that means that the period in this case is going to be 10 seconds. Okay, this 10 to 20. So we can find this out if we do k equals 360 divided by 10, and that's going to be a k value of 36. So now the phase shift, so this value inside here of d, is what's going to be changing whether we're looking at sine or cos. Okay, so for example, let's take a look at sine first. Okay, so let's rewrite our equation over here and fill in exactly what we're missing. So f of x is equal to, we know a, which is equal to 2. We're going to look at sine. Our k value is equal to, we calculated 36. Then we have inside here our x. We're going to leave this a little bit of a gap And we're going to have our, since this is positive 1, we're going to put plus 1 right over here. So I'm going to highlight now what our sign is going to be. So again, our sign is going to have this shape just like that. So how much was this sign? It usually starts right here. How much was it shifted over? Well, how much do these represent? Let's take a look. So if this is 2, 4, 6, 8, no, not exactly. So this it looks like it's 5 right here. So then let's see. Halfway between 5 and 10. So if this is 5, this is going to be 7.5. Okay, then we can start this right here. So if it's 7.5 to the right, we can keep this minus sign as part of the equation, and we can just simply put positive 7.5 in this line right here. Okay, so that's our example of one of our equations. Another one of these signs, though, I just want you to take a look at is, let's say, I'm going to erase this little bit of yellow as much as I can, because you can see we shifted it over a little bit. So what if, let's see if I can erase that, perfect. What if we used this part? So let's say we start a little bit lower, just like this, and we go up, and then it goes like that. So you can see this is kind of like sine, but you can see that it's going on the negative first. Instead of going upwards, it's going downwards, which means that vertically there's going to be reflection in the x-axis. So what we do is we stick a -2, and in this case, there's a horizontal shift of 2.5. And everything else stays the same of what we calculated earlier. So these are two perfectly fine examples that's going to give you the exact same function. So again, this is related to sine. So let's go ahead and do it for cos now. So let me erase this here as best as we can. Okay, so for cos, let's see. Okay, perfect. So let's take a look at this. So cos, we can actually start just right here. So it's at the top, it comes down just like cos usually does, and then cos comes back up, and now it starts repeating. So for cos in this case, we're going to have our general equation. F of x is equal to, because this goes downwards, okay, at the very start, that's what we expect. So we can leave that as +2, and then we're going to have cos 36x, and because there is no shift horizontally, it's simply just going to be that. There's going to be, I mean, you don't have to write +0, so we can just simplify this to be 36x plus 1. And we can leave our equation just like that. Okay, the other option that you could possibly do as another option for this is, instead of starting at the top, if we started here and it goes up instead and then down, and then the pattern starts repeating. So again, looking at this green shape, because it's a vertical reflection, we can write this as f of x. In this case now it's -2 cos 36x minus, and in this case, because we're shifting it to the right, you can see we're shifting this halfway between 0 and 10. This is going to be 5. It's going to be a 5 inside this bracket here, and then +1. So these are just a couple different examples And if you were to plot all of these on Desmos, you would get the exact same equation if you do want to check for yourself. Okay, this last example here is going to be giving us some information, and we're going to model this and create a sketch for it. So a group of students are tracking a friend, Jacob, who is riding a Ferris wheel. They know that Jacob reaches the maximum height of 9 meters at 10 seconds, and then reaches the minimum height of 1 meter at 55 seconds. Okay, so we have our maximum height, and we have a minimum height. So we want to determine a sinusoidal model for his height at any time. What this essentially means, this model here is an equation. EQN is a short form for equation. Okay, so what we're going to do is organize our graph first. That because we have a maximum height of 9 and a minimum of 1, we're going to label this over here the time, t, and this is going to be our h. And what we can do actually is skip 1 and label each of these 1. So each of these are going to represent 0.5. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and the top one is 10. For each of these here, each of these are going to represent 5. So we're going to skip this. This is going to be 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, so our first point, we have a maximum of 9 at 10 seconds. So at 10 seconds, we have a maximum point of 9. And we have a minimum of 1 meter at 55. So right here at 55, 1 meter, and it's going to look something like this. So this shape, in general, just as an approximation, is maybe going to look something like this, and then it's going to come back up, and then it's going to keep, this periodic pattern. Okay, so what we can do first, though, is find, okay, where is our axis of curve that splits this? Okay, so maybe we can do that perhaps just over here. So our C is equal to the max plus min divided by 2. So this is going to be 9 plus 1 divided by 2, which is simply just that value of 5. So going across just like this is where we're going to have our axes of curve. Okay, so that's the first thing that we can determine from the information so far. The next thing that we can do is find our amplitude. So our amplitude, again, we can see from these axes of curve to our maximum. So 9 to 5 is going to be that value of 4, and we can see from 5 to 1 is also that value of 4. So we have our A and we have our C so far. Okay, so the next thing that we're going to try to find is the period. Okay, so remember the K value is 360 over the period. So in this case, we were only given a maximum and a minimum. But this right here will represent half the period. We don't know exactly where the other point is just yet, but it would perhaps be somewhere over here that again is equal symmetrical distance. So to find this half a period, let's do that over here. Okay, we'll call this perhaps half P. What do we have? So this is at 55 seconds, and we're going to subtract, this one here was at 10 seconds, so in between that distance is 45 seconds. So if we did that another half over here, we can say that the full period is just going to be this 45 times 2, which is simply just those 90 seconds. Okay, so from this point, if we were to go 90 seconds, That's going to be right here. So 100 and we add 90, sorry, 10 and we add 90 is going to give us 100. So the other maximum, this pattern that it repeats starts going just like that. So to go back to our K value, we can simply just do 360 over 90, which is going to give us a K value of 4. So we have 3 elements so far. We're just missing that one, which is that D value. So what we can do is just do a bit of a rough sketch. So this is going to look something like this. And what we can actually do is make this a little bit more symmetrical instead of doing it just by hand. So 10 and 55, what is the halfway point of that? So that's 32.5. So this is 35 right here. So that's going to be right here. So what we can do is do something like this. And this is going to come around just like that. Oops. Whoa. Sorry about that. So we can go like this and connect this. And, oh, I'm not sure what happened exactly. Did it disappear? There we go. So let's connect this. And if we go from 55 to 100, what is halfway of that? 77.5. So this is 75. This is 80. 77.5 is going to be right here. So we can go something like this. And it's going to have this, it's going to kind of curve this way to have that shape. So again, what does this sort of resemble? And again, if we keep this going, it's going to then come downwards just like that. So you can see, hopefully, this is our cosine function, it kind of looks like. So let's use that as kind of our basis, all right? So we're going to have, in general, let's write our general equation. We have f of x is equal to a. In this case, we're going to use cos. We're going to have k x minus d plus c. And now we're going to use the variables given to us in this question. So we have height as a function of time. The a value we have is 4, and because it looks like our normal pattern that it's going downwards first and it's coming back up, there's no negative. So we have our cos, we have 4 again. Oops, sorry. X, we're going to wait for that shift, so let's leave a bit of a gap. And the c, we know is equal to plus 5. That's the axes of curve. Okay, that we're going out. So the question is now, how much has it been shifted? Well, you can see the pattern starts at this point right here. So the whole thing has been shifted 10 units to the right. So we keep this minus sign as part of the general equation, and we simply just put in positive 10. And that's what gives us our general equation to model this situation. Okay, so this is our part A. Our part B is asking us determine the height of Jacob here at 78 seconds. So what we can simply do, based off our model here, we're going to find out what this height is at a t of 78. So we have 4 cos, oh, that's my mistake. That k here is supposed to be 4. And let's plug in information. So we have 4. And the one thing we can do as well, again, my apologies, instead of x, we're going to replace that with t. This is our name for our x variable. So we're going to have cos 4, instead of t, we have 78 minus 10, and we're going to add 5. And we're simply just going to throw this in our calculator. So let's take it one step at a time, though. So 78 minus 10 we have is 68 plus 5. So 4 times 68 is 272. So if we do that, we get 4. And cos of 272, I just did this. Or maybe we can do this whole thing, actually. Let's do that. So let's do 4 cos 272. So this is 0.14 plus 5, and we get 5.14. So if we go to 78, which is approximately, right, halfway, 77.5, 78 is a little bit over, so that would be right there. Okay, so this right here. So this is our 78. So if we go up to our graph as a double check, and we go across, we can see, we can go this way, sorry, I should have went right to left, that this is approximately, 5, perhaps 0.14. So that's just a double check for us that our calculation or our model was correct. So we can say, therefore, the height of Jacob at 78 seconds is 5.14 meters.